So today we have the great pleasure of having Xiaojun Yao giving a seminar. So Xiaojun got his PhD from Duke in 2019, studying heavy ion collisions, quark-gluon plasma, and quark-cornea using effective field theories. In 2015, he got the AAPT Outstanding Teaching Assistant Award Prize. Then, after his PhD, he moved to MIT for a postdoc. And then in 2022, he joined IQuS as a research assistant professor. And today he will talk about his calculations on classical and quantum computers of the shear viscosity of lattice gauge theories. Please, Xiaojun, take it away.
Thank you, Mark. It's a great pleasure to give the talk today. And I will mainly focus on the work that I did with Francesco and Anthony, who are both former members of the IQuS. And our paper was recently accepted by PRD and is listed as an editor suggestion. It is better. Okay, so here's the agenda of my talk. I'll mainly talk about calculating shear viscosity using real-time Hamiltonian lattice approach. And I'll start with the motivation why we want to calculate shear viscosity. Then I will set up the numerical calculation and discuss a quantum algorithm to realize this numerical setup. And then I'll apply this setup to study 2+1D SU2 pure gauge theory. And in the end, I'll show you some classical and quantum results on a small lattice. Okay, so let me start with the motivation. And the idea is to study the deconfined phase of nuclear matter. So this is a phase diagram of QCD matter on nuclear matter. The y-axis is temperature and the x-axis is baryon density. And we know from the asymptotic freedom that at a sufficiently high temperature or sufficiently high density, the QCD matter becomes deconfined. And we start to see quarks and gluons rather than confined hadrons. So to try to understand the deconfined phase, people carry out heavy ion collisions where in the laboratory, they accelerate heavy nuclei and smash them. And during these collisions, there are a lot of particles produced. And people are trying to analyze the final distributions of these particles and infer if there is a quark-gluon plasma produced and also the properties of the quark-gluon plasma. So during the last 20 years, what we know is that the quark-gluon plasma is indeed produced in the laboratory, and its temperature is about 150 MeV at very small baryon density. And right now, there are still two collider experiments running. One is the relativistic heavy ion collider in Brookhaven National Lab, and the other one is a Large Hadron Collider at CERN. And in these collisions, we have an impact parameter. If we look at the reaction, we not always have head-on collisions between the two heavy nucleus. We may have collisions where the two nuclei just partially overlap with each other in this plane. And we call this type of collisions peripheral collisions, while the central head-on collisions is called central collisions, where the impact parameter is almost zero. And if we look at the peripheral collisions in this reaction plane, initially we have an almond shape in the overlapping region. As a result of this almond shape, the pressure or the gradient of density along this horizontal axis is bigger than that along this vertical axis. As a result, the particles produced along the horizontal direction gets a bigger push, and that's why they have a bigger momentum in the end. And this kind of asymmetric initial geometry leads to an asymmetric distribution in the azimuthal plane. And if we look at the final particle production in the azimuthal plane detected by this angle phi, we can actually decompose that distribution in terms of harmonics with different powers n here. And these different cosine functions can have different prefactors called Vn, and these Vn are called flow coefficients. And this asymmetric behavior is called collective flow, like particles flying out and they're interacting with each other. For example, when n equals 2, that V2 is called elliptic flow coefficient, and for 3, it's called triangular flow. And these flow coefficients have been measured in experiments. For example, this is a result from the ALICE collaboration, where they measured the charged particles produced from heavy ion collisions in both central collisions and the peripheral collisions. And you can see from this plot, in peripheral collisions where the asymmetry of the initial overlap is bigger, and that's why the V2 coefficient is bigger in the peripheral collisions. But they also measured V3 and V4 and find non-zero values. So this is an interesting experimental observation, and people try to understand this collective behavior in the final production. And one effective way to do that is to use relativistic hydrodynamics and solve the hydrodynamics to understand the collective behavior in the particle production. Hydrodynamics is just an effective theory describing long wavelength dynamics. So it's nothing but just momentum, energy momentum conservation. And what one needs to do is write down an effective description of the stress energy tensor T mu nu. And since we're looking at long wavelength dynamics, one can do a gradient expansion for the T mu nu for the stress energy tensor. For example, here, I write down the leading order term, which involves zero gradient in the expansion. It involves the energy density and the pressure, and also this fluid velocity U here. And at the leading order or linear order in the expansion, we have this shear term that is given by this expression here in the third line. And the prefactor of this linear correction term is called shear viscosity. And let me give you an intuitive feeling of the shear viscosity. So consider a two-layer fluid where the bottom layer of the fluid is at static, while the top layer of the fluid is moving at a constant velocity. And you can imagine as the top layer is moving, the fluid between these two layers will develop some non-zero velocity along this horizontal direction. And that velocity is varying along the y-axis. And this is caused by the friction force between different layers in the fluid. And the force between the different layers of the fluid is actually proportional to the area of the fluid, and also proportional to the gradient of the velocity along the y direction. And the proportional constant of this force is the shear viscosity here. And people try to solve the hydrodynamics and match with experimental data. So here is what they found. This is a V2 collective flow coefficient measured as a function of the number of particles produced. And the black dots in this plot are experimental data. And people try to vary the value of shear viscosity and see what is the best value that describes the data. And what they found from this simple exercise is that when eta, the shear viscosity over the entropy density S, is equal to 0.08, they can describe the data well. You can see from this plot. But this is a very small number in nature. And to give you a feeling about that, the eta over S, the shear viscosity divided by the entropy density is 1,000 for air. But for water, the eta over S is just 10. And this connects to our everyday feeling. Like you try to stir the water, you don't feel much resistance. That means the shear viscosity is small. But for water, that is 10. For the coagulant plasma, it's 0.08. And that's why people call the coagulant plasma almost a perfect fluid. And more recently, people do more systematic analysis of the experimental data. So basically, they use all experimental measurements on these Vn coefficients and use the Bayesian analysis, which is one type of machine learning, to try to infer the eta over S from the experimental data. So this is a plot where they confront the final theory prediction with experimental data. And this is the extracted eta over S as a function of temperature. And the band here corresponds to uncertainty band in this Bayesian analysis. All right.
I'm a little confused with this analogy you made.
Yeah.
Because so you say stirring water, the value is 10, and that's not much.
Right.
So I guess like the shear viscosity for QGP is low, but like for air, it's big. But air is like trying to stir the air, and I mean that's like nothing, right?
Yeah, but the density in the air is very low.
Yeah, okay.
It doesn't mean the different layers of air has smaller force. It just means just the density is too low. That's why you need to divide by the entropy density, which is a description of how many particles are in your system, right? Like the density of the particles.
Okay, so I shouldn't, okay, yeah, so I shouldn't directly interpret those numbers as like the viscosity itself.
Right, yeah,
okay.
Divided by some kind of reference.
So yeah, maybe, I mean, one thing that could be done and to give us a better intuitive picture would be to maybe list out the shear viscosity of a fluid that's a liquid that's known to be highly viscous, like honey.
Oh yeah, right, yes, that's a good point. I don't have the number in my mind, but I'll find that. Okay, let me come back to this shear viscosity extraction. The band here corresponds to the uncertainty band, but people also find that at low temperatures, the extraction from the experimental data agrees with the 1/4 pi calculation result from the ADS-CFT correspondence, which works for strongly coupled supersymmetric Yang-Mills theory. But people try to use it as a benchmark also for QCD. Okay, but that is experimental extraction or ADS-CFT calculation. How about calculating shear viscosity in QCD? It actually turns out to be very challenging to calculate shear viscosity in QCD. For example, we can try perturbation theory, and we know that at a sufficiently high temperature, the rounding coupling becomes smaller, and we should be able to use perturbation theory there. This was actually initiated by San-Yang Chuang and Larry Yaffe at the University of Washington in 1996. And in this plot, I show you the most updated calculation in QCD. First, let's look at a very high temperature, like 1 TeV temperature. When we change the calculation from leading order to next leading order, we still see roughly a factor of 2 change there. And that may indicate that perturbation theory, even at 1 TeV temperature, it's not working well. On the other hand, at very low temperatures, we have large uncertainty bands there. So that just indicates perturbation theory is not very reliable in accurately calculating the shear viscosity. And then how about non-perturbative methods in QCD, like Euclidean lattice QCD approach? In this way, we analytically continue the real time to imaginary time tau, and then evaluate this imaginary time correlation function of Txy on the lattice. And on the lattice, we directly calculate this correlation function. But to get the shear viscosity, we need to do an inversion problem here. So the G tau can be calculated on lattice, but the physics is included in the spectral function rho omega here. So we need to invert this integral expression to get the shear viscosity. But this is a highly non-trivial inverse process. It's actually mathematically ill-defined because we only have a finite number of data points from lattice calculation for G tau, but we need to invert it and get a continuous function out of it. So as you can imagine, different functional forms of the O omega will give you the same lattice data. And furthermore, the kernel involved in this inversion process has a property that it becomes a constant when omega is small. And that just means this inversion process is insensitive to the structure of rho omega at a small omega. So that makes the inversion even more challenging. Okay, so I hope I have convinced you that shear viscosity is interesting for QCD, but it's very hard to compute. So now we're going to discuss one way to achieve it, which is using real-time Hamiltonian approach. So what we're going to do is to calculate real-time correlation functions of the stress engine tensor, and then use this Kubo formula to extract the shear viscosity eta. So you can think of this Kubo formula as a matching calculation between the full theory QCD and the effective description, which is hydrodynamics. And this Kubo formula is kind of a tree-level matching equation. And the retarded correlation function involved in this Kubo formula is defined by the kind of commutator between two Txy operator. they're at a different time and a different position. There's also a theta function for the retarded propagation. And if we can calculate this real-time correlation function, then we can extract the shear viscosity. And this correlation function is defined at a thermal equilibrium, where this density matrix rho t here describes a thermal state, and the correlation itself is a real-time object. And here I just list the expression of the Txy or T mu nu for the 2+1D theory, the pure gauge theory. Okay, that's what we're going to do. We are going to calculate that real-time correlation function. And here is the quantum algorithm to do that. So the quantum algorithm consists of 4 parts. So first, the qubits describing the system are all in the 0 state. And we need to first prepare the thermal state because the correlation function is defined for thermal state. And in this work, we use the quantum invariant time propagation method to prepare the thermal state. This QITP method was first developed by the collaboration between the Trento group and the Lawrence Berkeley National Lab. But it was further developed by Francesco Turro to use it for thermal state preparation. And the second step in the circuit or in the quantum algorithm is to realize this commutator between 2 operators. And the method we do that is to use this expression here. So when the operator A is a Pauli string, one can show that the commutator between 2 operators A and B can be written in this way. So what we need to do in the quantum circuit is to involve the A operator with a phase pi/4. And after that, we just do real-time evolution. And in the end, we do measurements on all of the system qubits and do a reanalysis of the experiment. Okay, let me talk about the details of the thermal state preparation. So this is a detailed circuit for the thermal state preparation. In the beginning, we just have 4 qubits, like the first one, third one, fifth one, and seventh one, describing the system. But the first step is to prepare an infinitely temperature state or the maximally mixed state. The way we do that is we introduce ancilla qubits for each system qubit, and then we'll apply a Hadamard gate to each of the system qubit, and then apply CNOTs connecting the system qubit and the ancilla qubit. And after that, we just measure the ancilla qubit we introduced. It doesn't matter what measurements results we get from these ancilla measurements, but after the measurements, one can show that the state for the system becomes a maximally mixed state corresponding to an infinitely high temperature state. And then we do quantum imaginary time propagation, trying to cool that infinite temperature state. To realize this quantum imaginary time propagation, we need to introduce another ancilla qubit here, which is shown at the bottom of this plot. And then we just do a joint evolution between the system qubits and these extra ancilla qubits according to this unitary operator here. And after this kind of joint unitary evolution, we measure the ancilla qubits here. And if the measurements returns 0, then we know the system is now a thermal state given by this expression here. If the measurement of the ancilla qubit returns 1, that means the thermal state preparation fails and we need to restart from the beginning. Okay, and the rest of the steps is just to realizing that retarded Green's function. As I mentioned on the previous slide, we use this commutator expression to achieve the Txy calculation, commutator calculation. And more specifically, we have 2 Txy operators at a different time. And we write one of them, the Txy at the 0 time, as the sum of many Pauli strings labeled by this sigma alpha term here. And then we just apply the formula on the top, and we get this expression here. So this expression is very informative. It basically tells us that we first need to prepare the thermal state, and then we apply this sigma alpha term with a phase pi/4. And then we do real-time evolution. And after that, we just measure the system in a basis where the Txy is diagonal. And after the measurements, we can just reconstruct the expectation value of this operator. So mathematically, that just corresponds to this expression. So after the high over fall phase evolution and the real-time evolution, we measure in a basis where the Txy is diagonal, which in this case will correspond to the computational basis, and that makes sense easier. And after that, we just do a post-processing and extract this expectation value of the commutator. Okay, so that's the algorithm we're going to use. And now let me talk about application to the 2+1D SU2 pure gauge theory. So let me start with a brief introduction to the SU2 gauge theory. So we're going to use the Kugel-Susskind Hamiltonian. This has been derived long time ago, and the Hamiltonian consists of two parts, the electric energy part and also the magnetic energy part. The electric energy part involves the electric field operators, which lives on the links of the lattice. And the magnetic energy part consists of the plaquette operator, which consists of 4 Wilson lines, and they are just living on the plaquette of the lattice. And to quantize the theory, we need to impose how these two operators commute or not commute. For non-Abelian gauge theory, this electric field is actually a generator of the gauge transformation for the link variables. Like when the EA acts on the link variable, it generates the TA for the U for the link variable, and the TA is just the generator of the SU2 algebra. And for a non-Abelian group, these generators follow this non-trivial commutation relation. The FABC here is just the structure constant of the SUN group. But since we work with the Kugel-Susskind Hamiltonian, we're using the A0 equals to 0 gauge. That means we have remaining gauge redundancy. And for physical states, we need to project onto states that are satisfying this Gauss law, which basically says at each vertex, the sum of the electric field is 0. It means the state at this vertex is a singlet state in the SU2 group. And we're going to use the electric basis on the links. The state can be described as 3 quantum numbers, the angular momentum quantum number J, and the 2 third components, ML and MR, for the left end and the right end of the link variable. And the electric energy, E squared, in this basis is diagonal, and the value is given by J times J plus 1. This is very similar to the SU2 algebra that we learned in quantum mechanics. And we need to impose the Gauss law at each vertex. And the Gauss law says the state at the vertex is SU2 singlet state. And this is a very simple example of SU2 singlet state. For example, if we have 2 links with J equals 1/2, and we know from quantum mechanics that to form a SU2 singlet state, we just use an antisymmetric linear combination of the 2 states, 2 spin states. And this has been generalized to more complicated cases. For example, in the work by Natalie, Jesse, and Martin, they studied the plaquette chain for the SU2 theory, and they can uniquely project the states onto physical states because each vertex on the plaquette chain only has 3 legs. So this is not the case for the full 2D plane. If we use a square lattice, each vertex has 4 links. And then the SU2 singlet state is not uniquely defined by the 4 G values on these 4 links. One needs additional quantum numbers to specify physical states. And this is the motivation why we want to use the honeycomb lattice, because the honeycomb can still fulfill the 2D plane, also has the advantage that each vertex only had 3 links. And that makes it easy to uniquely define the physical states by just using the G values on the links. And then one can similarly work out the Hamiltonian on the honeycomb lattice. And in the electric basis, one can also work out the expression of the magnetic term. It is a generalization of the earlier work where people work out this term for square lattices. And the expression involves the Wigner 6G symbols. And basically, the expression is a product over all vertices of a honeycomb lattice. And for our calculation, we also need the expression of the Txy operator. And for the SU2 case, they're just given by this Ex times Ey here. And if we use the Gauss law, which says the sum of the electric fields is 0 at each vertices, we can express the Txy in this way. And since we're using the electric basis, both operators here are diagonal. So that's why the Txy operator in this basis is also diagonal. And that makes the calculation easier. Okay, so here is some systematics of the calculation. First, we want to understand the Gmax cutoff effect. And here I just study a 2x2 honeycomb lattice with a coupling fixed to be 1. And then I calculate the energy density and the entropy density as functions of temperature. And the different colors just correspond to different Gmax cutoff here. And we can see from this plot, for example, if we study, for example, when T equals 5, Gmax equals 1.5 is enough for the convergence of the energy density. We see little change from the green curve to the red curve here. And similarly for the entropy density. So in general, one can derive an upper bound for the Gmax one needs to do a physical calculation. If we want to describe all the states up to the energy E with an error, with an uncertainty epsilon, this is an upper bound of the Gmax we need. It's inversely proportional to the coupling and also inversely proportional to the epsilon. Sorry.
Have you also checked how does it differ in volume? Like if you go from 2x2 lattice to some other geometry, say ladder or even a bigger lattice, does the convergence get worse or better?
Yeah, basically, according to that expression, there's a volume factor showing in the numerator. So when you go to bigger lattices,
even if it is asymmetric, like even if it is not symmetric, like right now you have 2x2, even if you do the ladder, you still
yes,
okay.
Yes, right, that's right, yes. So yeah, I mean, it's a polynomial growing with the volume, but at the moment it could be a resource demanding thing. Yeah. Okay, and so in the rest of the talk, I'll just focus on the kind of simplest truncation because this allows us to do some calculation classically at the moment. We're going to use the Gmax equals 1/2 cutoff. And in this limit, one can actually map the system of SU2 gauge theory onto a spin system. For example, for the bare vacuum of the theory, we can just map it onto a spin system where all the spins are pointing down and each spin corresponding to the position of one plaquette on the lattice. And if one plaquette is now in the Gmax equals 1/2 case, then it actually corresponds to the spin pointing up. And if we apply another plaquette operator at, for example, at this 0, 1, then just flip the spin. And in this spin picture, we can write down the Hamiltonian completely in terms of polymatrices. It involves kind of single body term, two body term, and also a 7-body term for the plaquette operator. And this is what we're going to use in the rest. Okay, so I'm going to show you some results. First, some classical results. The way we extract the shear viscosity is to calculate this quantity as a function of real-time t and plot it as a function of time. And then we try to extract its asymptotic value at the infinite long time. The first plot just shows the finite size effect. First, it's a 3x3 honeycomb lattice labeled by this orange line, compared with a 4x4 honeycomb lattice labeled by this blue line. And in the 3x3 case, we just see some wild oscillations, and there's no way that we can extract some meaningful asymptotic value. But as we make the lattice bigger, like 4x4, we see the oscillation becomes much milder. And then we may try to extrapolate an infinite asymptotic value. So the second plot shows one example of the extraction when the coupling is 0.6. We still have some oscillations at the late time, but roughly they're oscillating with respect to a central value. Nikita?
How big is the Hilbert space here?
4x4 is 2 to the 16. So 65,000.
Okay.
Yeah. Yeah, I'll have more numbers on the later slide. Yeah, and basically that's what we do. We vary the temperature and also the coupling, and we try to fit this asymptotic value. And we also tried to do a naive continuum limit extrapolation, which is depicted in this figure. So we calculate the eta over S at the different couplings, for example, using 0.8, 0.7, and all the way to 0.4. And then we try to extrapolate towards zero coupling. According to the asymptotic freedom, zero coupling here corresponds to zero spacing, which is a continuum limit. And the renormalization group in this particular example has been worked out in this paper. So we just use these ansatz and try to do a continuum extrapolation. But I'm not claiming this is physical results. We have a lot of caveat because of the truncation of the local Hilbert space. But remarkably, we get the value that is very close to 1/4 pi. And then we tried several temperatures, which is labeled by this beta 0 in the second plot. And we try to get that zero coupling or zero lattice spacing results. Up to the uncertainties, we find consistency with the holographic results 1/4 pi. And the uncertainties is quite large when the temperature is small. Okay, so this is a kind of intermediate summary of the classical results. The Hamiltonian lattice formulation allows us to evaluate the real-time correlation functions to extract the shear viscosity, but we want to achieve a physical limit in the end. That requires us to take first the continuum limit, which means the lattice spacing goes to 0. At the same time means the coupling needs to be changed to 0. But according to the formula I showed you, this requires we do not do truncation of the local Hilbert space. The Gmax needs to be taken to infinity. And the second physical limit requires big volume limit or infinite volume limit. So we need to take the lattice size to be big. And finally, since we're using lattice, it breaks the translation symmetry of the continuum theory. So the T mu nu operator is may no longer be a conserved current. So that means we need to do some extra operator renormalization in the physical extrapolation. And this has been discussed in this paper, like how you define your operator for a better convergence behavior. So here are some numbers for the first two steps. The first two steps are already very challenging at the moment. For example, for a 4x4 lattice with Gmax equals 1/2, the Hilbert space has more than 65,000 states. If we try to make the truncation bigger, like on a 3x3 lattice with Gmax equals 1, the system actually has more than 500,000 states, which cannot be exactly diagonalized at the moment. And that's why we are thinking about quantum computing to calculate the shear viscosity. Okay, so now I'm going to show you some very preliminary quantum simulation results. So here, we are just doing a 2x2 honeycomb lattice calculation with the parameters set here. And we just calculate the imaginary part of this retarded Green's function as a function of time. And we tried simulators from the continuum and IBM with just 500 shots from the continuum simulator. We get a very big kind of statistical uncertainty band. That's just because the signal in the early time is very small. And to resolve the value of these correlators, we need a large number of shots. And we see that when we use the IBM simulator and using 10 million shots, the statistical uncertainty can be largely shrunk to these green bands here. And one can actually estimate the number of shots one needs is inversely proportional to the kind of error one set, and also proportional to a number that can be estimated once we have a lattice setup. But we expect that 10 million shots will be enough, because at later times, the signal will become bigger. And that's why we need fewer shots there for the same accuracy. And another potential challenge is the thermal state preparation, Because as I mentioned earlier, the thermal state preparation is not always successful. If it fails, we need to restart from the beginning. And this is a success probability of the thermal state preparation. And we find that we have an exponential scaling here with the volume of the lattice. That means if we want to do a big volume calculation, the success probability is exponentially small. But it's not that bad in practice, because we want to look at high temperature phase of the theory. And what does high temperature mean here? It means it's much larger than the typical scale of the problem. And the typical scale in my problem here is a global mass, which can be calculated by the energy difference between the first excited states and the ground state. And in my case, it's a 6.2. So much bigger than 6.2 corresponds to beta equals 0.1 or 0.05. And these numbers mean it's high temperature. And what we find is that at the high temperatures, these exponential decaying functions have very small prefactor in the exponent. So for a reasonable accuracy calculation, we don't need to go to infinite large volume. And that's why the success probability is still large. Okay, so now let me go to my conclusions. And in this talk, I hope I persuaded you that shear viscosity is very interesting for QCD, but very hard to compute at the moment. And we propose to use real-time Hamiltonian lattice approach to calculate it. At the moment, just using classical computing, we can do exact diagonalization up to 4x4 honeycomb lattice with Gmax equals 1/2. And our naive continuum limit extraction shows consistency with the holographic results 1/4 pi. And we also discussed the quantum algorithm to do the calculation on the quantum computer. And hopefully the quantum algorithm can take us far, and the future goal is to really achieve the physical limit for these calculations. Thank you for your attention.
So this is only pure gauge.
That's pure gauge.
Have you thought about including fermions? What's going to change?
Yes. For example, for the honeycomb lattice, one can add fermions basically like each vertex. But then since the fermions also carries SU2 indices, the projection onto physical states or SU2 singlex is more involved. And basically it's just a more involved tracking of your states. Sorry.
Can you go back to the plot where you showed the success probability of preparing the thermal
Yeah.
state?
Mm-hmm.
You said that for a given blue ball mass, you have flat curve which kind of saves you. However, are you computing that blue ball mass by keeping the same G's and just increasing the volume? Because if you want to take the true continuum limit, you also have to tune your G, and in that case, that blue ball mass will also change as you go or bigger and bigger. Because that I assume that's not the physical blue ball mass, that's like the lattice gap that you're looking at.
That's right.
That will change. And do you have any idea if you want to take the true continuum limit, how bad would the curve be?
So yeah, so this is not a physical mass, but we expect for this non-abelian pure gauge series, there is a gap in the physical theory. So in the end, you just look at temperatures much bigger than that gap.
But if you try to go to the next volume, and if that gap, if you have to tune your G such that that gap gets larger, or that gap changes slowly, but then your temperature creation cost might, the thermal state creation cost might grow up, right? Like,
so the global mass doesn't change with the volume much,
okay.
but it's sensitive to the coupling and also the Gmax. So, but when you change the coupling, your meaning of temperature is also changing. So in the end, it's the ratio between the matters.
Okay.
And you always define high as the ratio is bigger.
Okay.
Yeah. Sure.
So the paper that you guys already have out, did that also include the quantum results?
The simulator result.
Okay,
yes.
simulator, okay.
Yeah.
And that was with noise as well?
No noise. The uncertainty here are purely statistical from the sample.
Okay, do you know, I guess, have you like considered doing the simulation with noise to see kind of how that will affect the estimation of shear viscosity?
Oh, sure. Yeah, that would be interesting. I think it's in our future work.
Okay.
Yeah, and that's also important for, eventual calculation on the hardware.
Yeah, I mean, I think ultimately, I mean, I kind of expect that that's going to be the limiting factor.
Yeah, right,
Somehow. So.
right. Because these extrapolations does require you go to late time.
Mhm.
And yeah, that can be challenging. Yeah.
Have you considered the possibility, since one of the challenges is the preparing the thermal state, have you considered the possibility of mapping this to an analog simulator where you now have a physical notion of temperature where your system kind of provides you a bath, and maybe you can save some cost by doing an analog instead of a purely digital simulation?
I see. Yeah, I never thought of that way. I think the challenge is what kind of analog system can be versatile to handle different Gmax cutoff. I feel whenever I change the Gmax cutoff, my Hamiltonian is kind of changing, and the map onto the analog simulator will be changed.
If you restrict it to the Jmax equal to half, you'll probably find something, but then you have the advantage would be you can probably go to the larger volumes much easier than the digital one. That's like intuitively seems that reasonable. I'm saying like it's going to be difficult for higher Jmax, but Jmax equal to half, probably scaling the volume would be easier in a analog system.
Yeah. I agree with that. Yeah, right.
So did you bring up the analog approach in the context of like thermal state preparation? Because you're saying that you just kind of time all this, like it's easy to get to a thermal state because you're doing things analogically.
Yeah, so I have seen papers where if you have trapped ion system and it maps to a FIFO theory, then you can naturally use the warming of the trapped ion system as your temperature. So you naturally you can just introduce a little bit of less control instead of cooling your system, and you have a notion of temperature back.
And the state they have on those ion trap is also a mixed state.
Yeah,
I see. Okay.
I mean, there is a way to map it. I
see. That's interesting because ion trap also has all-to-all connectivity, which is good for these 2D simulations.
But you suffer a number of shots, right? Because preparing an ion system and then measuring it is expensive than the superconducting.
Yeah, I see.
Yeah. You want to conclude it?
Oh, okay. So if there are more questions, let's thank Xiaojun again.